Lecture 1-3 will discuss circuit elements and give the more formal definition for some of the elements that we've already been examining in the prior two lectures. We will also explain in more detail Ohm's law, power across a resistor, ideal voltage and current sources, and active and passive circuit elements. An electric circuit source is a device that is capable of converting non-electric energy to electric energy and vice versa. These sources can either absorb power or deliver power, generally by maintaining either voltage or current. Independent sources establish a voltage or current in a circuit without relying on voltage or currents elsewhere in the circuit. Typically, students are most familiar with independent sources because they've seen voltage and current sources in their physics courses. However, there are actually 4 other sources which are called dependent or controlled sources, and these establish a voltage or current in a circuit based upon a value for a voltage or current elsewhere in the circuit. Since these are unfamiliar, we will spend the most time discussing these. So let's discuss our 2 independent sources first. These sources establish a voltage or current in the circuit without relying on voltage or currents elsewhere in the circuit. The way that we identify them to be independent sources is that they are circles. The way that we identify this first one to be a current source is because the arrow represents the flow in current. And the way that we identify the second ideal voltage source is based upon the plus and minus, which represent the potential difference or the polarity of the voltage source. The first of the 4 dependent or controlled sources are at the bottom of the page. The way that we identify these as dependent sources is they're both diamonds. The way that we identify them as a current source is the arrow, or the voltage source is the separation of charge, or the plus and the minus. The first one is a current-controlled current source. It's current-controlled because the controlling variable is Ix, and the gain on that current is beta Ix. That means somewhere in your circuit you have a current defined to be Ix, and beta is the multiplier that gives you the current for the current-controlled current source. The second one is a voltage-controlled voltage source. I know it's voltage-controlled because of Vx, and the multiplier or gain is mu. That means somewhere in your circuit Vx must be defined, and mu Vx represents the gain. When you multiply those two, that gives you the value of this voltage source. These are called dependent sources because their value must depend upon a voltage or current elsewhere in the circuit. Notice that beta and mu are a pure gain and they are unitless. The final 2 dependent sources are the voltage-controlled current source and the current-controlled voltage source. Once again, we know they're dependent sources because they're both diamonds. We know the top one is a current source because of the arrow, and we know that the bottom one is a voltage source because of the plus and the minus. We know that it's voltage controlled because of Vx, which means somewhere in my circuit I've defined Vx, and alpha Vx gives me the gain for my current source. Now, since I'm converting a voltage to a current, alpha must have units of amps per volt. I know that the second voltage source is current controlled because of Ix, which must be defined in the circuit, and the gain, rho Ix, converts a current to a voltage, so it must have units of volts per amp. Now let's talk about active circuit elements. Active circuit elements are ones that model a device capable of generating electric energy. So our primary active circuit elements are the 6 that we just summarized, such as a voltage source and a current source. A passive circuit element models physical devices that cannot generate electric energy. Notice these are resistors, inductors, and capacitors. So although inductors and capacitors store energy and then release it back into the circuit, they must be storing that energy from one of our active circuit elements, such as a voltage or current source. Now let's try an example where we practice using independent and dependent sources to find values on a circuit. So for the first in-class activity, the question is, what value of Vs is required in order for the following interconnection to be valid? In order to answer this question, we have to discuss some things we haven't talked about in great detail as of yet, but we'll do it now. When you have 3 elements that are connected on both sides, being at the top and at the bottom, I'm circling their connection points. These 3 elements are said to be in parallel. When elements are tied together on both sides, they're in parallel. Elements that are in parallel have the same voltage. Because of this, which is based upon Kirchhoff's current law and Kirchhoff's voltage law, for this to be valid, all of these elements have to have the same voltage. Same polarity, same value. Positive on top, negative on the bottom. Positive on top, negative on the bottom. So for the first two elements, which are both voltage sources, the second one is a current-controlled voltage source. So in order to find the value of that voltage source, we need to go find the controlling variable I0. I0 is actually the current in that final element, the 8 amps. However, since I0 points down and the 8 amps points up, it's negative 8 amps. If they were pointing the same direction, I0 would equal 8 amps. Therefore, the value of the dependent voltage source is 6 times negative 8, which is negative 48 volts. So the voltage source is positive on top and negative on the bottom with a numeric value of 48 volts. Since I have two voltage sources in parallel, they must have the same voltage. Thus, Vs is also equal to negative 48 volts. Let's try the next activity. Here's our next vocabulary word, and it is series. When exactly two circuit elements are connected end to end, they are said to be in series. So in our case, the 8 amps is in series with the alpha Vx current source, and the 10 volt source is in series with the alpha Vx current source, and the 10 volt source is in series with the 8 amp current source. Elements that are in series have the same current, same direction, same numeric value. So what that means is that if I have a current source 8 amps that goes up, then I also have 8 amps that goes to the left, 8 amps that comes around counterclockwise and goes down into the 10 volts, and then the 8 amps returns at the bottom back to the source. So I have a voltage controlled current source here. So my first task is to find the controlling variable Vx. Vx is actually the voltage across the voltage source. Since they have the same polarity, Vx is positive 10 volts. Now my current source, which is alpha Vx, would be alpha times 10. However, our challenge is to find alpha, which we don't know yet. But since we know all of the current sources have to have the same direction and the same current value, I also know that alpha Vx must be equal to negative 8. Why is it negative? It's negative because the current actually is counterclockwise through that loop, but the current through the dependent source is pointing clockwise. So alpha Vx is equal to negative 8. So equating these last two equations, I get alpha 10 is equal to negative 8, or alpha is equal to negative 4/5. However, since I am converting a voltage to a current, alpha must have units of amps per volt. This concludes our demonstration of showing how dependent sources work as well as determining valid connections between circuit elements. So now let's talk about resistance. Resistance is the capacity of a material to impede the flow of current or the flow of electric charge. The circuit element used to model this behavior is the resistor. Many useful devices take advantage of resistance in heating, including stoves, toasters, irons, and space heaters. So the circuit element on the left is what you actually have in your parts kit and what you will use to build your circuits, and it's a resistor. However, the symbol that we use in class is on the right. And notice that it has a voltage marking as well as a current marking. The way that we describe the relationship between current and resistance for a resistor is Ohm's law, which we've talked about before. V equals I times R, where V is the voltage in volts, I is the current in amperes, and R is the resistance in ohms. We also talk about conductance sometimes, where conductance is measured in either Siemens or Mohs, which is an upside down capital omega. And the relationship between conductance and resistance is G is equal to 1 over R. There are several power relationships that we have already described, including P is equal to dW dt, or P is equal to V times I. Now that we know that V is equal to I times R, or that I is equal to V over R, we have 4 new equations for power. I squared R, V squared over R, V squared G, or I squared over G. Resistors are a passive circuit element. So one thing that it's very important to remember is that resistors always drop voltage, and resistors always absorb power. We represent the power relationship for a resistor as positive V times I based upon the way it's drawn here, and the numeric value for power should always be greater than 0. This shows us and helps us to remember that resistors always drop voltage and resistors always absorb power. So now let's bring together everything that we've discussed so far to show that the following 2 circuits obey the law of conservation of energy. Remember, this top circuit is an example of a single loop circuit or a series circuit where all of the elements are in series, and we would say therefore that they all have the same current. So our current is actually going to be 2Vx because this is our voltage controlled current source. Vx is the voltage across the voltage source, which is 4 volts, which makes the value of this current source 8 amps. So the 8 amps flows counterclockwise, and it goes up and to the left, around and down through the 4 volts, around and through the 5 ohms and back. Since resistors always drop voltage, and we always draw resistors to obey the passive sign convention, I put positive on the left and negative on the right. To obey the Ohm's law, voltage is equal to current times resistance, so that makes the voltage drop across this resistor 80 volts. Then I have a 4 volt drop across the voltage source because the current goes into the positive and out of the negative, and I come down here for the 5 ohm resistor. Since resistors are drawn to drop voltage, I put the positive on the left and the minus on the right. 8 times 5 is 40 volts. I now have the current and the voltage for each of the elements other than the dependent source. So I now want to show that it obeys the law of conservation of energy, and recall that we use a table to do this. So the first column of the table are the elements. The next 2 columns are the voltage and the current. And the final column is going to be the power. We'll do the resistors first. So the 10 ohm resistor has 80 volt drop and 8 amps through it. Then we have a 5 ohm resistor that has a 40 volt drop, and it also has 8 amps through it. Everything's in series, so all of my elements are going to have 8 amps. So I can go ahead and write 8 amps for the 4 volt source and 8 amps for the dependent current source. And I can write 4 volts for the 4 volt source. We'll hold off on doing the voltage for the dependent source for a second. Since resistors always absorb power, I know that I'm going to have 8 times 8, or 640 watts absorbed by the 10 ohm resistor, 8 times 40, or 320 watts absorbed by the 5 ohm resistor, and because the current goes into the positive and out of the negative, that's a positive voltage current relationship for the 4 volt source, and both of these are numerically positive, which gives me positive 32 watts. So even without finding the voltage for the dependent source, I know that if this circuit's going to obey the law of conservation of energy, that dependent current source better deliver power. But let's figure out how we confirm this exactly. If I want to know the voltage across the dependent source, I have to look at the voltage drops for all the other elements. This is called KVL, which we will discuss in more detail in the next lecture. And it states that the sum of the voltages around a loop must sum to 0. So if I have an 80 volt drop plus a 4 volt drop plus a 40 volt drop, I need a rise. And my rise has to be the sum of these drops, which is 124 volts. And that gives me the voltage across the dependent source. Since the current goes into the negative and out of the positive for the dependent source, that yields 992 watts delivered. Since the sum of the absorbed and delivered power sums to 0, we can say that this circuit does obey the law of conservation of energy. Let's try another one. The circuit at the bottom is called a single node pair. It's called a single node pair because all three elements are connected at a node on the top and at the bottom, and they're all in parallel. Remember, elements that are in parallel have the same voltage. Since there's only one voltage source here and it's 12 volts, that means all of these elements are positive on top, negative on the bottom, and have a value of 12 volts. We have a current-controlled current source that's 0.5 I naught, and the controlling variable over here is I naught. We can use Ohm's law to find I naught, which is 12 volts, divided by 4 ohms, which equals 3 amps. So now that I know the current down through the 4 ohm resistor is 3 amps, I know that my dependent current source must be 0.5 I naught or 1.5 amps. Okay, let's make our table. We're going to have elements in the first column. Then we'll have voltage, current, and the power in watts. We'll do the resistor and the independent source first. So we have 4 ohms, 12 volts, and then we'll do 0.5 I naught. The 4 ohm resistor has a voltage drop of 12 volts, as do all three elements because they're in parallel. The 4 ohm resistor has a current of 3 amps. Resistors always drop voltage and resistors always absorb power, so we know that the power for that resistor is 36 watts. The dependent current source has a voltage of 12 volts and a current of 1.5 amps. We just found that. And we know that that element, actually the current flows from the negative to the positive based upon the polarity of the voltage. So it delivers power, and it would deliver 18 watts. So based upon what we have so far, we know that that 12 volt source should deliver power, but let's see why. And the rule that we use to determine that is something we call KCL, which we'll discuss in more detail in the next lecture. KCL states that the sum of the currents into and out of a node is equal to 0. So far I have 1.5 amps going in and I have 3 amps coming out if I look at the top node. Therefore, I need 1.5 more amps to go in so that the sum of the currents into the node equals the sum of the currents out of the node. Based upon that, the 12 volt source has a current of 1.5 amps. Since that current flows from the negative terminal to the positive terminal, that would be negative 18 watts. Finally, you sum the powers. And what you'll see is that the sum of the power is 0, which means that this circuit does obey the law of conservation of energy. This concludes our discussion on Lecture 1-3, Circuit Elements.